Have you ever wondered about the mysteries of our universe? The vastness of space, the birth of stars, and the possibility of life on other planets? Today, we will delve into the fascinating world of space exploration and discuss the incredible James Webb Space Telescope. On the momentous day of December 25, 2021, a groundbreaking event took place. The world witnessed the remarkable launch of the James Webb Space Telescope, an awe-inspiring marvel that now stands as the largest and most powerful telescope in existence. This extraordinary creation opens up the possibilities of a unique form of exploration and an opportunity to delve into the depths of time. While we cannot physically journey back to the past, the James Webb Space Telescope offers us a glimpse into history unlike anything before. Prepare to embark on a journey spanning millions and billions of years as we unlock the secrets of our universe, reaching an astonishing distance of 13 billion years. This captivating telescope allows us to witness the very origins of our cosmos, tracing back to the momentous event known as the Big Bang, which occurred 13.8 billion years ago. With the James Webb Space Telescope, we can observe the universe as it existed only 0.7 billion years after its inception. But how is such a feat possible? Join me in today's video as we unravel this extraordinary phenomenon. One of the most extraordinary aspects of this telescope lies in its unique ability to detect infrared light. When we gaze at the sky through a conventional telescope, we perceive the wavelengths of visible light, the light that our naked eyes can see. Remember those lessons on the electromagnetic spectrum from our school days? It encompasses a vast range of electromagnetic waves, including X-rays, ultraviolet rays, radio waves, and microwaves, with a small portion dedicated to visible light. Typically, the telescopes available for purchase allow us to explore only the visible light wavelengths, spanning from blue to red, where red possesses the longest wavelength. As you may know, electromagnetic waves with longer wavelengths have a greater ease of passing through objects and obstacles, much like radio waves. This is why we can listen to radio waves even if they traverse through buildings. In comparison, infrared wavelengths are even longer than red wavelengths. However, we cannot perceive infrared light with our naked eyes. The advantage of utilizing a telescope to observe the infrared spectrum becomes evident when we examine a photograph. On the left, we have an image captured by the Hubble Space Telescope, our most potent telescope to date. In this image, we can discern space dust and formations of gas clouds. However, infrared wavelengths possess the capability to penetrate through dust and clouds, enabling us to witness what lies beyond. The image on the right showcases our envisioned view through the James Webb Telescope, a higher quality, high-definition picture, so to speak. The term infrared translates to below red from Latin, as it represents frequencies that lie beneath those of red light. Remember, frequency is inversely proportional to wavelength. Anything that emits heat, including humans, animals, the sun, and fire, radiates infrared waves. Consequently, night vision goggles utilized by soldiers are designed to detect infrared. Through these goggles, we gain a view enhanced by infrared cameras, capturing the infrared waves emitted by stars, galaxies, and planets, allowing us to observe them in all their glory. Another advantage of infrared light emerges when we consider the tremendous distances involved in observing stars that are billions of kilometers away from us. As the light from these distant stars reaches our telescope, it has traveled unfathomable distances. By the time it reaches us, and considering the gradual expansion of the universe, the wavelength of the light has stretched. This phenomenon is known as the redshift, a slight elongation and shift of the wavelength towards the red end of the spectrum. In the world of telescopes, the larger the mirror they possess, the greater the amount of light they can capture. Consequently, the resulting image resolution becomes significantly higher. To achieve this, advanced telescopes, including the James Webb Space Telescope, are equipped with larger mirrors. The mirror of the Hubble Space Telescope, for instance, was of a particular size. However, the mirror of the James Webb Space Telescope is even more extraordinary. This magnificent mirror is entirely plated with 24-karat gold, as gold possesses exceptional reflectivity for red light. Thanks to this golden coating, the mirror's reflectiveness reaches a remarkable 98%. Nevertheless, an obstacle arises with the James Webb Telescope. You see, just as everything that emits heat generates infrared waves, the telescope itself, once operational, will radiate heat, emitting infrared waves. This emission can interfere with the waves arriving from distant galaxies, potentially hindering the production of high-quality images. To address this concern, the James Webb Telescope operates at incredibly low temperatures, reaching as cold as -223 degrees Celsius. Achieving such frigid temperatures presents a significant challenge on Earth, where the temperature has not fallen below -89 degrees Celsius. However, in the vacuum of space, where sunlight is absent, it becomes feasible. You may be aware that if sunlight were to reach you in space, the temperature would rapidly rise, an occurrence we witness on the Moon. Due to the absence of an atmosphere on the Moon, temperatures may plummet to -170 degrees Celsius. However, when sunlight appears, temperatures soar to 120 degrees Celsius, causing severe problems for the telescope. To combat this issue, the James Webb Telescope is equipped with a remarkable sun shield. This shield, shaped like a kite and boasting the size of a tennis court, protects the telescope from the intense heat and light of the sun. The sun shield utilizes a specially crafted material called Kapton, which underwent extensive testing to determine its effectiveness in blocking the sun's rays and maintaining the telescope's cool temperature. Kapton is a man-made creation, and each of the sun shield's 5 layers consists of a thinness surpassing that of a human hair. Vacuum gaps separate these layers, further enhancing their efficacy. Additionally, each layer features an aluminum coating, while the 2 layers closest to the sun possess a coating of doped silicon. Unlike the Hubble Space Telescope, which orbits closely around Earth, the James Webb Telescope will be deployed a staggering 1.5 million kilometers away, at a point referred to as the L2 point. L2 represents the Lagrange point, located on the opposite side of the Sun. This strategic placement ensures maximum shielding from the Sun's heat and light, crucial for the telescope's optimal functioning. Moreover, the L2 point revolves synchronously with Earth, perpetually hiding the Sun during its orbit. Picture this. The Earth's shadow acts as a shield, preventing the Sun's illumination from hindering the telescope's observations. It is akin to when we struggle to see clearly when faced with direct sunlight. However, when we cover the Sun with our hand, our vision becomes sharper. A similar concept applies to the telescope. NASA has candidly stated that the process of creating and launching this telescope is incredibly intricate, leading them to identify over 300 potential problems that may arise. A single point of failure among these 300 issues would spell disaster for the entire project. A staggering $10 billion has been invested in this extraordinary endeavor, necessitating the reallocation of funds from numerous research projects to bring it to fruition. Collaboratively, NASA, the European Space Agency, and the Canadian Space Agency have joined forces to explore the immense possibilities that lie ahead. The scientific community eagerly anticipates the ability to study the formation of stars, galaxies, and other celestial bodies that emerged following the Big Bang. As previously mentioned, the James Webb Telescope offers a glimpse an astonishing 13 billion years into the past. In contrast, its predecessor, the Hubble Space Telescope, could only peer back roughly 1 billion years after the Big Bang, equivalent to approximately 12.8 billion years ago. The James Webb Telescope's unprecedented capabilities extend even further, enabling observations as far back as 0.3 billion years after the Big Bang. This is beautifully illustrated in the accompanying diagram, highlighting the birth of stars. You might wonder how it is possible to observe events from the past. The answer is elegantly simple. Light requires time to traverse vast distances. Consequently, by the time light reaches us, significant periods have passed. To comprehend this concept, let's consider our own sun. Sunlight takes approximately 8 minutes to reach Earth, covering a relatively short distance. In other words, if the sun were to suddenly vanish, it would take 8 minutes for us to observe its disappearance here on Earth. Therefore, when we gaze at the sun, we are effectively observing its state 8 minutes in the past. Expanding this notion to a much grander scale, when we peer at stars and galaxies millions of light years away, we are observing them as they appeared millions of years ago. The universe's vastness allows for the existence of stars located 13 billion light years away. By the time their light reaches Earth, 13 billion years have transpired, offering us a captivating glimpse into the events of our universe's distant past. Theoretically, this concept implies that if we were to teleport 100 million light years away from Earth to a planet situated at the same distance, we could construct an incredibly powerful telescope on that distant planet. From there, we would behold Earth as it appeared 100 million years ago, potentially witnessing the age of dinosaurs. However, a practical challenge arises. The time required to travel to the other planet would surpass the number of years we could observe backward in time. Consequently, achieving such teleportation capabilities would enable us to witness history unfolding on Earth, effectively embarking on a journey through time. Additionally, the James Webb Telescope holds the promise of discovering new planets. The possibility of encountering a planet with Earth-like conditions where life might potentially exist has captivated the scientific community. Time will reveal the extraordinary insights and discoveries this groundbreaking telescope will unveil. If you enjoyed this video, I invite you to explore another fascinating topic: wormhole. You can also browse my playlist of other captivating science-related videos. Thank you for watching, and I look forward to our next encounter.